Hello, can you hear me? Okay. So on-stack replacement is a very common technology for modern runtimes, and is used to support adaptive optimization, which is you might have a function that is currently executing and you might want to divert execution to another version of this function, and you might do it for optimization purposes. For instance, you have a long-running function and you are able at some point to optimize this function using profiling information, but at some point you might have to invalidate an optimization decision, and then you have to perform the optimization. And in this talk I'm going to refer to both kind of transitions as OSR. And the important part is that OSR has to preserve the intended program semantics, so it has to preserve the soundness of the whole execution. There's been quite a number of works in recent years on this topic from different groups. That's starting from our group in Rome, then the Oracle Research Group, the University of Lugano in Switzerland, Northeastern University, and Australian National University. So it's quite an active research area, I believe. And our contributions are the following. We try to look at OSR not just as an implementation problem, but more like a general means to transfer execution between related program versions. So the first contribution is a theoretical framework to explore soundness and feasibility of OSR, so which location it is possible to fire an OSR transition, and how can you actually combine multiple transformations, code transformations, while keeping the OSR feasible. And then we discuss how to implement these ideas in a general purpose compiler. We use LLVM as a running example. And finally, we discuss, and I think it's a the nicest contribution from this paper is showing that OSR can be valuable also outside the classic scope of VMs, and we show how these techniques can be used to improve the debugging of optimized C code, in particular with respect to these variables that might hold inconsistent values compared to what you're expecting at the source level because you have applied optimizations. So let's start with the language framework that we use in our paper, and we start with a very minimal imperative language where we have assignments, conditionals, go-to instructions. But in the implementation, then we add support for memory operations and function calls as well. So for the theoretical part, we start with a very tiny language. And in particular, we reason over this language by using computation tree logic, which has been explored in previous research to both reason about program properties, but also to express program transformations. For instance, there's here a definition of the liveness of a variable in terms of all the backward and future execution paths through some statement, or you can write a simple dead code elimination rule. Here we say that you can delete an assignment at location M if for all the control flow paths going through this location M, there is no eventual use of the variable X, so the statement is trivially dead. The goal for our OSR framework is, of course, to allow for transparent execution transfers. But what about reality? Where do runtimes employ OSR? So when you have to optimize some code, you have to jump into a better version of the code, you can postpone the OSR till you reach some point where the state realignment is simple. Think of a loop header or just a method call. But for the optimization, the story is different because you have to decide where to perform the optimization, and one strategy will be to put an OSR point for each instruction that may actually cause the optimization, and this approach was followed in Hotspot. Or you can decide to group OSR points, and in this case you resume from the last instruction that has externally visible effects. So you can discard all the intermediate results that are not externally visible, and this is the approach they have in GRAL. But we wanted to explore OSR at pretty much any program point, so for arbitrary program points, for two reasons. First reason, and might be relevant for VM architects, is that you might enable further optimization opportunities and also improve code generation for the de-optimization target. But the other reason, which I believe is more important, is that doing so, you pave the way to other applications of OSR. We discussed one in this paper, which is optimized code debugging, but there are other possible, and I'm going to talk about obfuscation later. So we propose an abstraction that is the OSR mapping with compensation code. A mapping encodes all the machinery that you need to transfer execution from one location L in your currently executing program P to an equivalent program point L prime in another version of this program P prime. And you're going to need a compensation code C that will fix the memory store that you have in program P in order to resume execution in P prime. Compensation code takes as input the memory store that you have at the source and has to compute the values that you expect to have at the OSR destination for live variables. Okay, why just the live variables? So in the paper we show the intuitive claim that the output of a program starting from any location and any memory store, it's only determined by the values of the live variables. So only the live variables determine the outcome of the execution. And more generally, with the mapping, you are able to capture all the relationships that you have between two related program versions. And what you can do is you can make each code transformation OSR aware by building a mapping as you transform the code. These mappings are usually bidirectional, which means you can transition back and forth from the two code versions. And the nice property is that mapping can be composed. So which means that you make transformations OSR aware, and then you can combine them in arbitrary ways, so as you like. Of course, you can write manually some OSR mappings for certain classes of transformations, but we try to see whether it's possible to generate mappings automatically. And we identify a class of code transformations for which you can do this, and we call these transformations live variable equivalent. So a transformation is LVE if for any program point and for any execution, you know that the variables that are live, both in the original and in a transformed program, they must hold the same value. I'm focusing only on the variables, the live variables that are in common. So this means that you can have also variables, live variables that are not present or are dead in the other program version. But this property, LV, is a natural property of many optimizations that they add instruction, delete, or move them around. We show that transformations such as constant propagation, dead code elimination, and loop invariant code motion are LVE, but in practice we try this also on transformations such as common sub-expression elimination that are LVE as well. So I was saying that there are some variables that are live but are not in common, and what you can do to reconstruct these live variables at the OSR target. So we propose an algorithm, Reconstruct, that is able to, actually it attempts to reconstruct a missing live variable by looking for a unique reaching definition of this, if there is a unique reaching definition for this variable at the OSR target. If there is such a definition, we try to compute the assignment, and we check whether we have the constituents for this assignment. If we do, we can just add to the compensation code the assignment. Otherwise, we have to reconstruct the constituents as well. So this algorithm is recursive. So in a nutshell, you build a compensation code that tries to compute the value that the variable would have had at the OSR target if you had been carrying execution in the target program from the beginning rather than in the original program. And I'm going to show you an example. So on the left here, we have a very unoptimized code. And on the right, we have a much shorter equivalent version of it. And how we obtain the optimized version? Well, first, if you look at the way that we assign variable a, we use the remainder operation, which you know that you're going to get no negative value for it. So if you use this information, you know that the else branch is trivially dead. You're never going to have a negative value for a, so you can remove it. And then you realize that variable d is now constant, and you can perform constant propagation. Also, you're not going to use b anymore in the program, so you can remove the assignment to b. And eventually, you can also delete the if branch for the second if statement, because d will always be 20, cannot be greater than 100. So you get this tiny code on the right, and now suppose that you want to de-optimize back to the unoptimized version. So we want to do this, for instance, right before the function call that assigns variable e. So if we look at the live variables in the optimized program, we have only one live variable. At this point, we have variable a, while in the unoptimized program, we have three variables. We have a, C, and D. So since the transformations that we use are live variable equivalent, A is already holding the correct value. We have to focus on reconstructing C and D. Well, for D is easy. D is a custom value, so we can just start with the compensation code and instruction D equals to 20. But what about C? So is there a unique reaching definition for C? Yes, we have one, which is C equal A plus B. But do we have all the constituents for this instruction? Well, we have A, but we don't have B, so we have to perform a recursive call, and we try to reconstruct B as well, and we can do it. Actually, we compute B in terms of A, and then we compute C, and in this way, we have a compensation code for the entire OSR transition. How we do this in practice? So we explore an implementation in a general purpose compiler, and we argue that you only need to add some probes while you transform the code. You have to track when you add an instruction, when you delete an instruction, when you move instructions around, or when you replace operands or just uses of the instructions. There are some compilers like Growl that they give this to you for free. In LLVM, we had to add a little bit of instrumentation by hand. And we came up with two versions of the reconstruct algorithm. There is one version, which we call it live, and uses for building the compensation code only the live state. And then we make another version, avail, which uses also some other variables that you have already computed, but they become dead meanwhile. But if you spill them, you can use them in reconstruct. So we instrumented a number of LLVM passes, and the number of lines of code that you have to change is actually little, which is about a dozen lines of code, and we had a number of probes ranging from 1 to 10 in the worst case. The hard part here is not adding instrumentation. It's more like figuring out what each optimization pass is doing. While for building the mapping between IR objects, we did it in about 300 lines of C++ code. And we try to assess on some benchmarks from these suites how many program points are actually eligible for an OSR transition, and we are able to perform OSR pretty much at any program point, especially when we use the second version of the algorithm. The compensation code, the size of the compensation code is typically small. It's about 12 instructions. And the number of variables that you have to spill is in the order of 2 or 3 to support the extra OSR points that are represented by the top bars here in this charts. But I want to talk now about our case study. It's a feasibility study on how to use OSR for a context that is not the usual managed runtime one. So we all know that when we have to debug a statically compiled program, we should not use optimizations. And the reason is that, okay, there is a clear conflict because optimizations, they're going to alter all the structure and the intermediate results of a program, while a debugger is striving to provide the user with the illusion that you are executing one source statement at a time. And if you try, for instance, to use GDB on a program compiled with optimizations, and you say, okay, print me the value of variable X, GDB may say, oh, sorry, it's been optimized out. But in some cases, you may get misleading values. So what can you do? Well, sometimes you really need to debug an optimized program, because you might have, for instance, that some bugs they do not surface in an unoptimized translation, while optimizations expose them. This is a classic. Or you might have race conditions that emerge only when you have efficient code, or you may have platform-specific constraints, so you cannot actually afford to run an optimized code at all. And what can you do? Well, okay, first problem statement. So in the literature on source level debugging, they say that a variable is endangered when, because of the effects of optimizations, this variable can hold at a breakpoint a value that is inconsistent with what you're expecting if you execute the program at the source level in the unoptimized version. And this might be due to instructions that you move around, deleted instructions, or just because the compiler performs register allocation and you end up clobbering some variables. A symbolic debugger has two options. Either it can be truthful and just warn the user that some variable might hold an inconsistent value, or, and this is nice, can try to provide expected behavior, showing the user how the variable would have looked like if you had carried execution in the unoptimized program. And if you're thinking of constraining optimizations for the sake of debuggability, or you can say, okay, I'm going to add some extra code to support debugging, that's not really an answer, because you end up running and debugging a suboptimal code. So what can you do? Okay, we try to use OSR to fix these endangered variables. And this idea was somehow explored in the implementations of the self-runtime in the 90s, where they used dynamic de-optimization to support debugging. And the idea is that OSR was used pretty much as a barrier to optimization, so you could optimize your code between OSR points, and at OSR points you were able to inspect the program state in terms of its source code. We try to elaborate on this idea by having by not restricting optimization. So we run unhindered variable equivalent transformations on all the C benchmarks in the spec suite. So we analyze each function in each benchmark. And we realized that actually quite a number of optimized functions, they are affected by this endangered variables problem. And in particular for such function, on average, 1 every 4 program points has at least one endangered variable, so the problem is quite real. And we try to see how good is Reconstruct at fixing, at providing expected behavior for these variable values. And we compute a recoverability ratio that attempts to measure how many endangered variables you can recover for each program point in each function, and then we compute an average for the entire benchmark. With the avail version of Reconstruct, we are able for half of the benchmark to reconstruct 95% of endangered variables. For 9 out of our 12 benchmarks, we get 90%. And in the worst case, we only get 83% of reconstructed variables. And the number of spills that you have to make is rather low. So to summarize the contributions of this paper, we tried to distill OSR to an abstract code morphing problem. We identify sufficient conditions for an OSR transition to take place in a sound manner. We have a constructive approach with our Reconstruct algorithm for LV transformations. The required changes to a compiler are quite small, I believe. And we show that OSR can be valuable in other areas as well. We have some future directions in mind. One will be to improve our algorithms to reconstruct more variables. Another will be to explore trade-offs in for instance, there is a very nice SQL paper that is about performing loop tiling in the presence of exceptions. So this paper shows that you actually have to log some state in order to support the optimization. And these trade-offs are largely explored in the OSR community. So how much logging you have to perform to support that many more extra points. And finally, we are thinking about further applications of OSR. In particular, I'm working on a project on dynamic diversity for software obfuscation. So for obfuscation, for instance, there is a commercial compiler that is able to generate statically a number of equivalent versions of the same function, and just at runtime, it will just pick different versions of it in order to hinder reverse engineering attempts. So if you put OSR in the picture, you can generate many equivalent versions and have a non-deterministic transition that has many program points as you want between this code. So I believe this could hamper reverse engineering attempts even more. This concludes my talk, and I'd be happy to answer your questions if you have. Thank you.
So I'll start with the question. So you mentioned there's this LVE property, right? The live variable equivalence. Are there optimizations that don't satisfy that property?
Yeah, I mean, there are heavy-duty transformations. For instance, on loop, if you perform loop reversal or loop tiling, any heavy-duty transformation, you might have that some variables will have inconsistent values. And we believe that you can come up with specific algorithms for those classes of transformation, and in the end you can combine the mappings for this transformation through program composition with the mappings that you're able to generate for the LV transformation over this passes. And yeah, I mean, in general, there are some countermeasures that you can apply. And another thing is that there are some optimization more dynamic, like I don't know, when you perform escape analysis. So our framework, for instance, doesn't account for it yet, but I think for implementers it will be pretty easy to add the code to materialize an object when you perform the optimization. So yeah, that's a nice, there are some nice opportunities for improving this approach for other transformations.
Any other questions? So let me ask another one. So in the abstract, you actually said that it's, you have basically it's a provably correct framework. So I just want to know a little bit more about the provably correct part.
Oh, yes.
What kind of correctness? I mean, yeah. What's the property and what kind of proof was there?
Okay. So you're asking about the mapping or the transformations?
Either one.
Okay. So the idea, I'll start first with this. So this is pretty much the main theorem of the entire framework, and here we show that pretty much if you start from any program store and program location, and you apply the, I mean, transitively the semantic function, you reach the final state of the program, and to prove that the final the output of the program that in the framework we define in terms of live variables on the last instruction, the output instruction. So you have to prove that the live variables have to be the same for any programs that for any state for which the live variables are the same. And for doing this, we perform we show inductively that if you do this on every instruction in our framework, which are
Sure. So I mean,
this, you preserve this property for every instruction that you execute. So in our big step semantics, you're preserving this at every step.
I was thinking more, does it look like a traditional proof of correctness? Is there any kind of thing different there? Was it difficult in a particular way?
Well, we use program by simulation.
Okay.
It's pretty plain, the proof. It's just, it's not automated. That's something that we would have liked to do.
Okay.
And there is a work, actually, it's a work of yours, I think, on parameterized program equivalence that we would like to explore to automate these proofs, but for now they're by hand. They're done by hand.
One more.
Mm-hmm.
I hope this is quick. So you are, or the way your framework is set up formally is talking about optimizations from one language to another, or one language to itself, rather.
Yes.
How much of it could you use in the context of maybe a JIT where you have a very high-level language up here and you want to swap back and forth between?
Okay, well, we're relying on an intermediate representation, so we work at IR level. If you are able to lower these different languages on this eventually on the same IR, you can use this framework right away. I haven't been thinking actually of different IRs to put them together. I should think about it, but in principle, if you are able to maintain the mappings between the different IR, it should be just a matter of translation, but not a theoretical problem, I think. But we can speak offline if you want.
Yeah, thanks. Great talk.
Thank you.